Hello everyone. Einstein's theory of general relativity tells us that mass and energy curves spacetime. So the overall matter-energy distribution of the universe must have an effect on the universe as a whole, giving it a curvature, a shape, with tiny variations here and there. So what shape is the universe? To be frank, we do not have access to the entire universe. The finite speed of light puts on a limit to how far we can observe, giving us the observable universe. What's outside of the observable universe? We don't know, and the dark reality is that we may never know because light simply can't catch up. But if we make an educated guess, and a really good one, it's probably just going to be more of the same kind of space and stuff. To some extent at least. After that it's just, we don't know. What we do have access to is our little corner of the universe. And what we can try to do is to extrapolate the curvature that we measure in our part of the universe to the entire universe and sort of try to predict what the overall shape of the universe might be. There's a big fundamental flaw in this argument, as you shall see, but let's just go with it for other insights that would follow. So let's say we measure the curvature of this part of the universe and find that it's slightly positive. What would that mean? Well, it could mean that maybe the universe, the entire universe as a whole, is a lot like a sphere. A sphere has positive curvature. There's a catch though, because a sphere is a three-dimensional object, and our universe is already three-dimensional. So if it's curved, is that a 4D version of a sphere or something? And does that mean that the universe, something beyond universe, is four-dimensional? No. That's not what we mean. The curvature we talk about in general relativity is the intrinsic curvature, not the extrinsic one. For instance, a sphere has an overall positive intrinsic curvature. There's no way you can represent a sphere on a flat surface. All these word maps lying around, they are a lie. Or put in a better way, they are projections that are not the truest representation of what that sphere, in this case the Earth, is. Different projections preserve different qualities, but none of them preserve everything of a sphere. Sometimes the sizes are all distorted and all. We are not getting into that. Anyways, one of the features of intrinsically curved space is that you don't have to leave it to conclude that it's curved. In contrast, think of a cylinder. It does seem like it has some curvature, and it does have a curvature, but the curvature there is extrinsic. It comes from the folding of the surface in a higher dimension. There is nothing that you can do from the surface of the cylinder that will tell you that the surface is curved, unless you are in a higher dimension, in which case you can just look. But in general relativity, the curvature we talk about is the intrinsic curvature, not the extrinsic curvature. And you don't need a higher dimension to curve that space into. Coming back to the curvature of the universe, the way we can find it, well, there are different ways. First, we can use triangles. Triangles have this very neat property that on a flat Euclidean surface, the sum of the interior angles add up to 180 degrees. But in positive curvature, they add up to more than 180 degrees, and in negative curvature, less than 180 degrees. So they are a very good way of checking if your surface has curvature or not. In the case of the cylinder, if you would have done the same exercise, you would have gotten a flat surface. Really, try it out. And how do we do that for the universe? By measuring these triangles from the light emitted from the very early universe, the cosmic microwave background. What we find is that coincidentally, the universe is very flat. That's okay. There's nothing that stops the universe from being flat, but it does seem quite a coincidence, because it could have curved any which way. It could have had any positive curvature, any negative curvature, but it has no curvature. There are other methods as well to get the curvature of the universe. For instance, we can take the value of the energy density of the universe and plug it into the equations of general relativity, and there too we get the same flat universe. And here again, if the universe would have had a little bit more or less energy than it actually has, the universe would have curved one way or the other. Theories of cosmic inflation try to explain this by hypothesizing a period of exponential expansion in the very early universe, and they have been very successful. So the universe is flat. Or is it? I mean, now we're going to talk about the fundamental flaw that we had in this argument, and which is that we do not have access to the entire universe. All the reasoning that we did applies to only our part of the universe, the observable universe, the universe that we can observe. However, the entire universe could be curved with a part of it being relatively flat. Similar to how the Earth looks pretty flat from the ground, but look it from afar and you'll see the curvature. But again, we don't have access to the entire universe. It could still be that the entire universe just is flat. But it doesn't have to. For all we know, there are so many possibilities for the shape of the universe. It could be flat and infinite, so it means an infinite universe, a universe that goes on forever, or it could be flat and finite, but that would require a different topology. So as of now, the possibilities are quite endless, and I think they will remain endless because we'll never have access to the entire universe. What we can talk about though is the observable universe, and it's pretty flat. I mean, the uncertainties are like very small, and we are pretty sure that it's almost flat, if not flat. Now, I want to conclude with the fact that there's a reason we call the observable universe the observable universe, because with known laws of physics, it is the edge of our vision. Even things happening outside of the observable universe now would never be able to influence us, because, well, at the boundary of the observable universe, space expanding faster than the speed of light, so nothing can really get to us from outside ever. So even in theory, we cannot go beyond, unless, of course, if faster than light is possible, then anything's possible then. Thanks for watching.